Okay, we're back to talk about more examples from friction. And these next examples that we'll do in this video are more typical. Not that the other ones weren't, but these are typical questions that I would say you definitely could expect to see on a Regents exam. Or questions like this. A man wants to push a 300 Newton wooden box across a wooden floor. Okay, notice already that they're telling us what type of materials we're dealing with. Will the box move if he applies a force of 100 newtons to push it? Show why or why not. Okay, so this is an interesting question. If he puts a 100 Newton force on it, it's a decent sized force, will the box move? Well, let's see. If this box is stationary, if he wants to push it and he wants to see if he can get it to move. If this box is stationary, then how big of a force do we need to make it start moving? We need to push with an applied force equal to the maximum force of static friction. What we really need is to push with a force just barely greater than the maximum force of static friction. But does that mean 1 more Newton of force? Does that mean 0.1 newtons of force more? Does it mean 0.01 newtons of force more? You can go down that rabbit hole all you want. Eventually what we end up saying is we just need that force to be just barely bigger than the maximum force of static friction. Mathematically, it works out that it's easier to just say we need that applied force to be equal to the maximum force of static friction. So let's figure out how big that is. Okay, what is the maximum force of static friction? Here's our box. Here's our axis. We're going to have a pretty standard free body diagram for this case. It's just a man pushing something across a floor. Fn points up, Fg points down, Fa and Ff. Our net force equations in the x direction. Fa minus Ff equals max. And again, to just barely get this object to start moving, we need to just barely give it an acceleration. So that acceleration is basically as small as it can possibly be. Basically, that acceleration is almost zero. It's just barely bigger than zero. But again, do we want it to be 1 meter per second squared, 0.1 meters per second squared, 0.01 meters per second squared? You just need that acceleration to be just barely bigger than zero, which means it's basically zero. So in order to simplify things, what we do is we say we want the acceleration to be zero. We want it to be just barely zero, okay? Just barely above zero, which is close enough to that we can just call it zero, okay? And since we're dealing with the maximum force of static friction, we therefore say that since this is zero, we need the applied force to be equal to the maximum force of static friction. The equation for Ff is mu Fn, so I'm going to write in this case, we need the applied force to be equal to mu times Fn. Now, mu for a wooden box that is not currently moving, it's at rest, and we're trying to get it to move, so we're dealing with static friction, wood on wood, static friction, the number is 0.42. But again, we don't know the normal force, so we need to go find that. To find that, I need to use the y direction. F net y equals Fn minus Fg equals may. Hopefully this logic is starting to get easier for you. The box doesn't say anything about the box accelerating up or accelerating down in the y direction, therefore the acceleration is zero, and therefore Fn equals Fg. Now I could write that Fn equals mg, but in this case, I just need to know what the normal force is, and I'm told that the normal force is equal to the force of gravity, or that's what I've found out. Well, look at this. The man wants to push a 300 Newton wooden box. What does that 300 Newtons mean? That's not the mass. Mass is measured in kilograms. That's the weight of the box. That's the force of gravity on the box. So guess what? I just found out that the normal force is equal to 300 Newtons because the force of gravity is 300 Newtons. So the applied force necessary to get the object to start moving is 126 newtons. Now, will the box move if he applies a force of 100 newtons? No. He needs a force of at least 126 newtons to get the box to start moving. So no, the 100 Newton force will not get the box to move. And actually, we just did B. What's the minimum force needed to get the box to start moving? We just solved it up there. We did all the work up there. The applied force needed to get the box to start moving is 126 newtons. So let's say that the guy does that. He gives that much force. If he continues to use this force once the box is moving, what will the box's acceleration be? Well, all the forces, they're not going to change here. Okay, what forces are acting on the box aren't going to change. All I need to do is I need to figure out, okay, if he continues to use this force once the box is moving, what will the box's acceleration be? I have all the same forces, the sizes might have changed, so I can still use this free body diagram and this net force equation. I want to know what the box's acceleration is in the x direction. I'm going to write down my F naught x equation. F naught x equals Fa minus Ff equals mu, or m, ax. If he continues to use this force, meaning the force he used to get it to start moving, 126 newtons, once the box is moving, what will the box's acceleration be? So he's using 126 newtons of force. Oh, what about the force of friction? Now, what's the difference? Now it's moving. So what must have changed? Well, if it's moving and it was formerly at rest, then the coefficient of friction changed from static to kinetic, therefore lowering the force of friction. Remember, force of kinetic friction is usually is less than the force of static friction because the coefficient of kinetic friction is less than the coefficient of static friction. For wood-on-wood kinetic, the coefficient is 0.3. So if I write this down, mu Fn, I'll be able to plug in mu as 0.30 and Fn as 300 from before. Now I do have an issue with the mass. I don't know the mass yet. But remember, I was told what the force of gravity on the box is, Fg. Therefore, I can find the mass. If Fg is 300 newtons, I have the mass, times g, the acceleration due to gravity, 9.81 meters per second squared. I find that the mass is approximately 30.58 kilograms. And that's getting multiplied by ax. So I have 126 minus the coefficient of kinetic friction, 0.30. The normal force acting on the box is 300. That hasn't changed. The surface isn't pressing up any harder on the box just because it's moving now, or less hard, equals 30.58 ax. I'm going to solve this by multiplying these two, 90. I take 126 and I subtract 90. I get 36, and then I divide by 30.58 to get ax by itself. What I come up with is 1.18 meters per second squared is the acceleration. Another similar question that can be answered with a net force equation from the same free body diagram. What force will he need to apply to keep the box moving at a constant velocity? So once it's moving, this would cause acceleration if he used all this force. How would he get the box to move at a constant velocity? Once again, net force equation. If it's moving at a constant velocity, that means the acceleration is 0, which means we just want the applied force to be equal to the force of friction. Now, the force of friction is the force of kinetic friction. We already kind of figured this out. Force of kinetic friction is mu Fn, mu being the kinetic coefficient of friction, that's 0.30, and the normal force is 300 newtons. The force needed to cause this to move at a constant velocity is 90 newtons. Okay? Needs to match the kinetic force of friction. Last question for this example. While he is pushing the box, another person places a 100 Newton weight on top of the box. What force will the man now need to apply to keep the box moving at a constant velocity? So you're putting 100 Newton weight on top of the box. The 100 Newton weight adds to the force of gravity that's acting down on now our two objects combined. So what was the force of gravity before? It was 300. Its weight was 300. Now, the force of gravity on our objects is 400 newtons. And guess what? Since the force of gravity was equal to our normal force, that's still the case here. Fn, the normal force, is now 400 newtons. So we apply the same reasoning that we did in the last question. F naught x equals Fa minus Ff equals max. We still want to keep it moving at a constant velocity, which means our applied force is equal to the force of friction, which is equal to mu Fn. We want to keep it moving at a constant velocity, so mu is 0.30. The normal force, since we added some weight to it, that's going to increase the normal force as well. That's now 400 newtons. The applied force needed to keep this object moving at a constant velocity has increased because that normal force has increased. The applied force now necessary is 120 newtons. So this just goes to show that typically when you add mass to a system, it will increase the normal force, which typically increases the amount of friction, the force of friction acting on that object. A few more examples. Number 4, a skier has a mass of 65 kilograms. Oh, why is that not focusing? There we go. A, if the skier coasts on a flat level surface, and by coasts I mean not moves at the same speed the whole time. What I really mean here is they're not pushing with their poles. What is her acceleration? Okay, we want to know her acceleration. I know the mass, I do not know the net force on the skier. And I don't know velocity, I don't know time, I don't know any of those things. That means, since I can get the idea that this might be a forces problem, I need to draw a free body diagram. So here's our skier. Here's our axis. We know there's a normal force pointing up. We know there's a force of gravity pointing down. And since the skier is just gliding over this surface, they're not pushing forward, there is no applied force on the skier. She's not pushing, she's not using her poles to push herself forward. Nothing is pushing her forward. She's just gliding, she's coasting. And since there's friction acting on her, you could think of this as she's just coasting to a stop. There is no force in the positive x direction. She's not pushing herself forward by any means. She just happens to be moving forward because of what happened before the beginning of the problem. She must have got speed some way, either going down the hill or pushing. Now she's just gliding, okay? So what happened before the problem does not affect the free body diagram now. She's just gliding. That means that there is no applied force pushing her forward, okay? And she's on a flat surface. There's simply friction pushing her back. There's nothing wrong with this free body diagram. Okay, there's absolutely nothing wrong with this. You don't have to have, sometimes people fall into this trap of thinking you need a force in each direction. You don't. You only need forces in the direction that there actually are forces. Okay? Since there's no applied force, we don't write it down. Nothing is pushing her forward. If we're then going to write our net force equations, they would look like this. F net x equals, let's see, positive x directions to the right, ff is to the left. That means this has to be negative ff equals max. And F net y is Fn minus Fg equals may. So clearly, in order to get the force of friction, or in order to get the acceleration, I need to calculate the force of friction. I know that the force of friction is equal to, since this is moving, we can use this equation, mu Fn equals max. Let's go back to our y equation. We're going to be able to find mu very easily. We just looked that up in the table. We need to know the normal force. The skier is not accelerating up off the surface or down into the surface. The acceleration is 0. Stop me if you've heard this before. Fn is equal to the force of gravity, which is equal to mg. Fn equals 65 kilograms times 9.81 meters per second squared. So the normal force must be equal to oh, I did that wrong. 65 times 9.81. 637.65 newtons. The coefficient of friction between waxed skis and snow is 0.05. Fn is 637.65 newtons. The mass of the skier is 65 kilograms. We're solving for Ax. Don't get freaked out by that negative. The acceleration is negative 0.4905. What does the negative mean? Look at your axis. You said positive was to the right. This just means that the skier is accelerating to the left. If they're moving to the right but accelerating to the left, they're slowing down. This makes sense. If you're just gliding to a rest on skis, you're probably slowing down over time. B and C are kinematics problems. Once you know the acceleration, it's very easy to figure out the answer to these kinematics problems. If the initial speed of the skier was 10 meters per second, that's VI, how long time would it take her to fully stop? VF is 0 meters per second. That's a fiat question. VF equals VI plus AT. If this is 0, the initial speed is 10 plus our negative 0.4905 meters per second squared acceleration. Solve for t. 10 divided by, oh, I guess technically it would be negative 10 once we subtract it over to the other side, divided by negative 10 divided by 0.4905 negative. We get a time of 20.39 seconds. It will take the skier 20.39 seconds to slow down. You actually have an option for C. You could either use the D equals VIT plus 1/2 AT squared equation, or VF squared equals VI squared plus 2AD. I'm going to use the second one just because I know that that will actually be easier. You can try using the first one, D equals VIT plus 1/2 AT squared, and see if it works out for you. You should get the exact same answer. I know the final velocity is 0. I know the initial velocity is 10 meters per second squared plus 2, negative 0.4905 meters per second squared. And how much distance would she have covered during this stop? D, that's what we're solving for. So I square 10, I get 100, I subtract to the other side, so I have negative 100 divided by 2, divided by, okay, let's actually just do this. 2 times 0.4905, 0.981, we're going to do negative 100 divided by 0.981, and we end up with a distance of 101.94 meters. That's how much distance she covers while she's stopping. Hopefully there's nothing in her way, because that's a really long time to stop. Our last example is another question that's very commonly comes up on Regents, or even on homeworks and practice Regentses, okay? It's a question that gives you a lot of information. You're asked to find a few different things. This is very reminiscent of, let's say, a free response or short answer question. You've got an object. You're told that the mass is 10 kilograms. The acceleration is 1.4 meters per second squared to the right. You're given two forces that act on this object. Applied force, 20 newtons to the right, kinetic friction to the left. We don't know how big that is. Obviously, there's a couple other forces here, but they're not drawn in. The block in the diagram above is in motion and being accelerated to the right. Find the net force on the block, the force of kinetic friction on the block, and the coefficient of kinetic friction for the block on this surface. Okay? Remember, coefficient depends on the two surfaces. If we were to move this block to another surface, the coefficient would be different, and the acceleration might be different as well. But in this case, we're looking to solve for this case in particular. The net force on the block. Now, don't immediately go and try and set up a free body diagram. Let's see if we can solve this without using a free body diagram. It's kind of implying that we're looking for the net force in the x direction. The net force in the y direction is pretty obviously 0. This object it doesn't say anything about this object accelerating up off the surface or down through the surface. So it's a pretty safe bet the net force in the y direction is 0. This is asking about the net force in the x direction. And it turns out that we know that. F net x, we know from Newton's second law, equals m/ax. The x is just meaning direction. We know the mass, and we know the acceleration in the x direction. We should be able to calculate F net x. The mass is 10 kilograms. the acceleration is 1.4 meters per second squared to the right. So the net force is simply 10 times 1.4, which is 14 newtons, and I'll put in parentheses to the right. Okay, easy, one-step solution. If we want to know the force of kinetic friction on the block, well, we could solve for that if we knew mu and if we knew the normal force. Turns out we don't know either of those. So what we're going to have to do is actually draw out a free body diagram and write our net force equations. I'm going to draw my free body diagram over here. Here's the box, or block, or whatever they call it. Here's our axis. We have normal force pointing up. We have force of gravity pointing down. We have an applied force to the right. We have kinetic friction, FF, to the left. Time to write our net force equations. In the x direction, we have FA minus FF equals MAX. We're looking for kinetic friction, so we're looking to solve for FF. This is important because, look, we already know a lot of information here. We know the mass, we know the acceleration, we even know the applied force, and we just found the net force in the x direction. We know everything in here. But be careful, don't try and substitute in everything you know. Just pick two parts of this equation and use those. For me, I already know the net force is 14 newtons. I'm going to write that equals FA minus, or no, excuse me, not FA. The applied force is 20 newtons minus FF. I could have put in 20 newtons minus FF equals 10 times 1.4 meters per second to the right, but then I just have to calculate that all over again. Okay? Pick the parts of the equation that are most useful to you. Once you write the net force equation once, fully, you don't have to use every single part of it. You can pick and choose the parts that are useful to you. Solving for FF means I'm going to add FF to both sides, and I'm going to subtract 14 from both sides. The net result is that I get that the force of friction is 6 newtons. The force of kinetic friction is 6 newtons. Now, if I'm solving for the coefficient of kinetic friction for the block on this surface, that means I'm looking for mu. Let's see if I can solve this equation. FF equals mu Fn. I know FF. I'm looking for mu. I don't know Fn yet. All that means I'm going to do is I haven't yet written the net force equation in the y direction. Fn minus Fg equals may. The block is not accelerating in the y direction, so that's 0. So we have Fn equals Fg, and therefore Fn equals mg. I'm going to plug in the mg right into this equation. FF equals mu mg. You don't have to do that if you don't want to. You could solve for the Fn up here and then plug it in. I'm just trying to save us a step. 6 newtons equals mu times the mass of 10 kilograms times the acceleration due to gravity of 9.81 meters per second squared. Make sure you understand the difference between g, the acceleration due to gravity, and the acceleration of the object. They are not the same thing. You need to know the difference between those. I multiply 10 times 9.81. I get 98.1. I divide that to the other side. So I do 6 divided by 98.1. Mu is 0.06. And that's what the coefficient of friction is. Okay? That's a very typical problem that you might see on the Regents. Friction is a little complicated, but hopefully you have a better idea of how to deal with it now. If you have any questions, please let me know. I'll see you for our next video on Newton's third law. Bye.